Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And within that playlist, I'm creating little mini-series depending upon what analysis we're doing or design of experiment we're doing. Here, this mini-series, we're doing analysis of covariance. And we're in part 2 of this little mini-series. And we're going to look at the column spaces of the design matrix. Now, in part 1, we introduced the model, which was y equals x star beta star plus epsilon. So it is a general linear model. But then we partitioned it into, so this design matrix, we partitioned it into what we call the ANOVA design part of it, and it's in a balanced fashion. And the z is the regression aspect, or the covariance. And then these are the parameters associated with those. Notice in every design matrix there's a mu, so there's a column of ones here. Now it is balanced. Why is it balanced? Well, it's balanced so we can create orthogonal column spaces, and that becomes important later in this mini-series. So now we want to explore this. So if we take these and multiply it across, this comes down, that comes down, the air term is here. And we're adding 0, and it's called adding a well-chosen 0 to the model. Now, if you add 0 to the model, it doesn't change it, so the column space has not changed one bit. So now we regroup them. So we group these two terms here, and then what's left over here. And we, the matrix multiplication aspect here. But now we want to look at this piece a little bit further. Notice that M is the perpendicular projection matrix on the column space of X. So the column space of X deals with the ANOVA design matrix. So when you pre-multiply any vector by it, it shoves it down into that column space of X. That's what a perpendicular projection matrix does. So if we look at MXZ, it shoves Z down into the column space of X, right? So if we look at this augmented matrix, X and MXZ, if we look at that column space, really this is already in the column space of X. So this is in the column space of X. It's one of those duh moments once you see it though. Now, the properties of perpendicular projection matrices, if you take I minus that perpendicular projection matrix, it projects it onto the orthogonal complement space of whatever the perpendicular projection matrix projects onto, which is the column space of X. So I minus MX is the perpendicular projection matrix onto the orthogonal complement of the column space of X. So I minus MX, Z, is orthogonal to the column space of X, right? This is a perpendicular projection, takes any vector and shoves it down into this column space. So it happens to be the column space orthogonal to X. So that tells us that X and I minus MXZ are orthogonal, right? This is in the orthogonal complement space, and of course, this column space of X is, X. So now, we can rewrite this MXZ. If it's in the column space of X, that means that we can write it as some linear combination of the columns of X, right? So MXZ can be thought of as X alpha. And this is for some alpha. So looking at this piece here, which we'll bring down here, and if we do that matrix multiplication, we get this. But this can be thought of as X alpha, so we can replace it, and then we can left factor out an X. And what we have in here are all unknown parameters. We don't know them. So when we add them, we still get a vector of unknown parameters. So let's just call that delta. So the column space here can be thought of as X delta. Now we're going to take this piece into this model and replace it with this. And that's what's on the next page. So this goes into that place. So we actually haven't changed the model. We haven't changed the column space of that model. Now we can sort of unmatrix multiply, right? If we were to multiply this out, then we get this back. But look, we're back into that format. This is, X in quotes, and this is beta star, star in quotes. So it's a linear model. Now, we'll use this model here to find the least squares estimates for gamma. We'll call it gamma tilde. Then we'll use gamma tilde to find the least squares estimates for beta in the original model. And this is what the next video is going to deal with. Now, perpendicular projection matrices onto this column space. So really, we would love to know the format of the perpendicular projection matrix onto this column space. But note that X and I minus mxz are orthogonal. That means the perpendicular projection matrix onto that column space, let's call it M, is the sum of the perpendicular projection matrices onto these individual column spaces. So the perpendicular projection matrix, the perpendicular projection matrix on the column space of X, we called MX. We've already examined that. Now the perpendicular projection matrix onto this column space is, we're going to call it M sub I minus mxz. We're just, whatever's here, we'll put as a subscript. Like we did here, we just used X as the subscript to M. So then we take this column space, and then it's that transpose times it, and since that's a perpendicular projection matrix, it's idempotent, so we just have one of those. And then it's this column space transpose, which is this. And of course, this is symmetric. And now I have a video called The Sum of Perpendicular Projection Matrices. I have it in my matrix playlist and my general linear models background playlist if you want to look at that. So the perpendicular projection matrix M onto this column space is the sum of these two perpendicular projection matrices, and that's because these spaces are orthogonal. Now this will be important in upcoming videos, but for now that's all I have. So hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.